that clock is only 5 minutes slow. It's usually ahead. All right. So in physics, if I were to write down some things, I'm going to write down some items here. My first question to you is, what have I written down? Any guesses? And I'll take guesses in the chat.
Random numbers.
I got somebody that says random numbers.
Days in a year, days in a week.
Okay, so I've got some people that say days in a year, days in a week,
Hours in a day.
hours in a day,
Seconds in a minute.
seconds in a minute. Well, the first response, random numbers, was absolutely correct. That was absolutely correct. Now, they weren't chosen at random. They were actually chosen because I did want you to come up with 60 minutes in an hour, 60 seconds in a minute, 365 days in a year. Because most of those, because those are common numbers that we use, most of you had a conversion factor in your head. Now, I said that absolutely right is because in physics, those numbers are random numbers until you put a unit on it. And then all of a sudden, those numbers have meaning, right? So, in physics, and keeping your units and doing unit analysis is going to save your tushy. Okay, it's going to save your tushy. So one of your homework problems that you're going to have is going to be something like this. So we're going to say distance is equal to velocity times time. And if I use distance, typically in physics we're going to use x to represent distance or y to represent distance. Velocity we're going to use v, and time we're going to use a t. Well, distance, because if I'm using units of distance, if I'm in the metric system, that's going to be meters. If I'm in the English system, that's going to be feet. But it could also be kilometers. It also could be miles. It could be a variety of different things. But my units for distance are going to be meters. My units for velocity will be in meters per second. And my units for time will be in seconds. So if I'm doing distance as velocity times time, I'm going to have meters is equal to meters divided by seconds times seconds. My seconds cancel out, and I have meters equal meters. And all of a sudden, I know that I have written my equation correctly, because I can't add apples and oranges. So one of your homework problems will be something like this. I've got distance is equal to acceleration times time, and you're asked to do the unit analysis for that. Well, let's do the unit analysis. Acceleration is going to be meters per second, which will allow us to write that as meters per second squared. So on this side, I've got meters, and now I've got meters per second squared times seconds. One of those cancel out, so I've got meters per second, and my unit analysis is not correct. I haven't validated that my equation is correct. But as we get into physics and as we get into working with our equations, one of the ways that you can tell that you're on the right track is by keeping track of your unit analysis. Because I will get some folks that will say, well, wait a second, we've not gotten that equation yet. We're going to come back to these. So let's look at force is equal to mass times acceleration. All right, and so that will be an F is equal to MA. Mass is going to have units of kilograms in our vernacular. But I will have kilograms times meters per second squared. That unit right there is going to be something that we call a derived unit. And that's going to be a unit of force, and we're going to give it a name called a Newton. But you may be given the equation, I've got force is equal to mass times velocity. Well, that's a kilogram meter per second squared, and that's kilograms times meters per second. Those units do not match. So the purpose of the homework problem that you have in WebAssign is just to start looking at both sides of the equation. Do I have units that match? And being able to do the unit analysis. Because as we start to do this, if I've got my distance is equal to velocity times time, and we want to solve for time, I'm going to have x divided by v is equal to t, and let's say I screwed it up because we all have done it. We were doing something fast, or we're trying to do it without, we're trying to do our homework on the computer without using a piece of scrap paper. And I might have written x times v is equal to t. Well, I can check that now. This is meters times meters per second. That gives me meters squared over seconds. That is not equal to seconds. So I've done my algebra incorrectly. And this is really, really going to help you out. But if I do this, that's meters divided by meters per second. And remember, if I have 1 over some value, that's going to give me the value. So my meters cancel out, I end up in seconds, and it shows that I've done my algebra correctly. So there's your first way to check, are you doing things right? The other thing is when I will tell you, because we've actually done the study, Dr. Otto, who is our institutional researcher, actually used my physics classes for her PhD dissertation to look at how you all think about math. And how you put that math back into that physical meaning. And it turns out you second guess yourselves. You're on the right track, and then you talk yourself out of the right answer. So one of the things you guys do this, I'm going to tell you, if you don't hear it, if you get a nickel for every time I say it, don't make it too hard. Don't make it too hard. Because you guys are going to make it harder on yourselves. You're going to be on the right track, you're going to have it all correct, and then you're going to go, well, it can't be that simple. And you're going to overcomplicate it. But this is one way that you can use to validate and check what you're doing. So we're back to numbers have units. So we've talked about this one. So 60 seconds in 1 hour is a conversion factor. Is a conversion factor. And hopefully we all remember, so I'm going to do 8,000 hours. And I want that in years. I want to know how many years that is. Okay? Well, we've got our conversion factors. I've got 60 seconds in an hour. I've got hours in a day. I have days in a year. So let's go ahead and do that. So I have 8,000 hours. I'm going to multiply it by a 1. There are 24 hours in a day, so I want days on top. And I have 24 hours on the bottom. My unit analysis is going to help me do that conversion. So I'm going to be able to cancel out my hours. I'm going to do it step by step instead of doing it on a long train. And that's just so that we can keep things tracked. The other thing is, when we're doing physics, you're going to need to make sure you understand your calculator. Some of your calculators do things in fractions, which drive me crazy. But you'll also want to do that. You'll also want to understand your method of operations on your calculator. There's one of the calculators that, if you're not careful, it's not as prevalent in Physics 1 because our calculations are pretty easy. But when you get to Physics 2, making sure you understand your method or your order of operations in your calculator, there are times that it's literally how you punched it into the calculator. So we're going to divide that by 24. So now my 8,000 hours is 333.3 days. I know most of you, not everybody, has taken chemistry. And we understand significant figures. If I'm teaching chemistry class, I get really, really persnickety about significant figures. Taking physics class, we are going to account for significant figures in a number of problems. And one of your homework problems is literally how you put it into WebAssign. And it's more dealing with how you put it into WebAssign. But it's asking you to do things, just a number of significant figures. For most part, on your tests or in other places, there are going to be some homework problems where watching your significant figures is really important because we're trying to demonstrate something. But most of the time, if you give me 0.1 or 2 past the decimal place, that's fine. I don't want to see 10 past the decimal place because remember, significant figures tell you the accuracy or where the error is in your number. It tells you where the error is in your number. So one of your homework problems, so let's go ahead and finish this and then we'll come back to one of the homework problems. So we have 333 days and we want it to be in years. So we were going to do that. So I have my days. And we know there are 365 days per year. So we'll leave that in the calculator, divide by 365, and now I've got 0.91 days per year, sorry. So I've done my conversion. My conversion factors are 1s, and I can always multiply a number by 1. All right, so the speed of light is something like 2.9969. I'm making these numbers up because I don't necessarily remember it to the 5th or 6th decimal place, times 10 to the 8th. You have a homework problem in WebAssign that's going to have you write down your speed of light to various numbers of significant figures. In WebAssign, if I'm typing this in WebAssign, so if I want this to 2 significant figures, I'm going to do 3.00 e to the 8 is how you're going to type that in to WebAssign.
So those are the same thing?
Those are the same thing. This one's to 2 significant figures, but WebAssign is going to want you to use this format. If I'm writing it to, this is to 3 significant figures, sorry, this is to 3 significant figures. I'm going to do this to 4 significant figures. I'm going to do 2.996 e to the 8. That's how WebAssign is going to want you to put it in. Now, again, I probably don't have my digits correct because I don't remember the speed of light to that many significant figures. I look it up. But I wanted you to know that that's the format. That's the format for the homework problem. Okay? Alright, so let's come back to my random numbers. So, my random numbers I picked, they weren't totally at random. As you guys already figured out, I gave you conversion factors, but why do I have 27? Anybody know why I have 27?
27 weeks.
27, well, yeah, but what's 27 weeks?
There's like a 50 in a year.
There's 52 weeks in a year. Now, actually, you're very familiar with 27, but it's not, and this is where we're talking about being able to understand, does a number make sense? So if I told you, if we did a calculation and we said a turtle, a turtle traveled so far in a unit of time, and we end up and we're calculating velocity, and so velocity is going to be the distance divided by time, and we said it's a turtle. And I give you that the turtle is now going at 27 meters per second. You need to be able to tell me that that's one heck of a turtle, and it's obviously a superhero turtle, and we're playing with cartoon physics. We don't necessarily think in meters per second. That's not how we interpret the world. But if I told you, you would do that calculation and just go on, that's what the numbers tell me. Because you don't have a frame of reference to understand that 27 meters per second would be cartoon physics turtle. But if I told you the turtle, our velocity of our turtle was 60 miles an hour, all of a sudden you go, no, that's cartoon physics. 27 meters per second is roughly 60 miles an hour. But because we don't necessarily think in meters per second, you don't have a frame of reference to gauge whether or not that value would make sense for a turtle. That value would make sense for a car, but it wouldn't necessarily make sense for a turtle. So that's one of the reasons why I randomly put out that 27, is I want to start giving you those rules of thumb that you have in your head, that you can say, am I playing the right game? Am I getting the right answer? We all have them, but we don't, if I do a calculation and I say I'm throwing a dart, and I end up with the answer that my dart, I'm throwing it, my dart traveled 100 yards, something's wrong. Either I'm a really good dart thrower, or I have a dart gun in order to get a dart to go that far. We know what we have in our head, what 100 yards looks like. We have in our head what 10 feet looks like. We know that the distance of a normal door is roughly between 6 and 7 feet. So you have these things in your head that allow you to say, am I in the right ballpark? Is my number in the right area? Am I getting something? And so and most of our physics problems in our book are going to be reasonable answers, so that you have a chance to look at it and validate your answer. Another thing I need to tell you about WebAssign, that'll help you out. I'm not seeing any questions in the chat, so I'm doing pretty good. Is when you're doing your homework, at each problem you'll see something like this. You'll see a CP, you'll see a number, you'll see a decimal point, and you'll probably see like an 036. Here's the crash course code. This says it's whatever Cengage book it is. It's the abbreviation for your book. And this is college physics, so that's the abbreviation for your book. This tells you the chapter it's from. This tells you the problem number in the end of chapter questions. Because hopefully by now you all have figured out that if I go to my end of my chapter questions, they're grouped by section in the chapter. So if I'm doing problem 36 and I go in and I look and this is like the introductory section, this will be like estimates, this will be like this, and now I know 36 is in there, I know which section to go back into the chapter to find my reading material. The other thing is we also know that we usually have odd answers to the back of the chapter questions in the back of the book, right? So this gives you a way to go without using a WebAssign try. And it gives you the answer so that you have a chance to work it out. Also in WebAssign, you have the opportunity to practice another. I recommend you do so. So that you can actually get the practice in there. But that is the code for deciphering that little gobbledygook associated with the homework problem. Now for some of you that will help, for some of you that won't. I also encourage you, reading a physics textbook is like poking your eye out with a needle. Sorry, it just is. It's a fact of life. I don't think I have ever sat down to read my physics textbook my entire career and sat there and read it start to finish. I start with the problems and go back and look at them. Okay, that's what I do. That's how I do it, because what the physics textbook is doing is giving you the derivation of where did this equation come from, great, and you have examples. Our textbook has really, really good examples, and the way our textbook is constructed, you can cover the answer and do the work of the textbook, or do the solve. It gives you the problem logic solving of that. And so you can actually cover the answer and work those examples. And I will point out which examples you really, really want to go back and look over and over and over again, because we're going to use that model multiple times. So that's what's there. But I do use our textbook, so you do want to go in and look at that. Another thing I need to coach everybody on is this. So this is our lovely y and x coordinate system. Okay, and when I do my lovely y and x coordinate system, I can draw something like this, and we all know that that's going to be x and y. But for some bizarre reason, your algebra book never tells you what that is. Some people will write it in this notation, but they've never told you what this is. This is a vector. It has a name. It is a vector. Vectors are special. Your algebra book has taught you how to work with this all over the place, but it's never told you its name. It's like the Lone Ranger, the Masked Man. They never tell it. So vectors are special. Vectors have magnitude and direction. Our vectors have magnitude and direction. Magnitude is how long it is. Direction is, where's it pointing? We can add vectors. So we're going to go ahead and look at this. can represent my vector this way. My vector can be represented with an R to give me my magnitude and my angle. So I can represent this as an R theta. I can represent this as, we're going to go ahead and give ourselves some information here. This is our X and this is our Y. We can represent it as our X and Y. I can also write this vector, we're going to give it a name, and that's usually how we're going to represent our vector and our vector notations. We put a little arrow over the gizmo. A unit vector in the X direction is an I. My unit vector in the Y direction is a J. And my unit vector in the Z direction is a K. That's our Z direction. And just for everybody's information, I do use a Latin 7. I do use I put my line in the Latin 7 so that it's a little clearer as to what things are. So unit vectors have a magnitude of 1. So right now I could write this A in a vector notation that says this is xi plus yj. Because when I add vectors, I can add them head to tail. So here is my x vector, here is my y vector, and that gets me to the same point. So now I have, this is what's known as polar coordinates. These are our Cartesian coordinates. This is my vector notation. But again, your algebra book, you've played with these things before, but they just have never told you it was a vector. So when we add a vector, so I'm going to do an add a vector, so we add vectors head to tail. And this would be a resultant vector. So this is my resultant vector. And I can add them head to tail. Just making sure I'm not getting something in the chat. Okay, we're good. All right. I can also add vectors mathematically. So vector A would look like this. Vector B is going to look like this. And my resultant vector is going to be A plus B, and it's going to equal so again, it's the things that you've seen before. It's just that your algebra book never gave you its physical meaning. It never told you that that's what you were trying to do. go back to this lovely. So I have my vector. And we have my triangle. Okay, we got something that looks like this. This is actually called a projection. Your x and y's are projections. But we also know right angle trigonometry. So this side is, if I do it in my xy situation, I'm going to say it's y, but I'm also going to use it as the opposite. This is, we've got listed as r, but this is also our hypotenuse. This is our x, but to this angle, this is going to be the adjacent. Now there's a reason why I do it in terms of opposite and adjacent and the hypotenuse, because in physics we can do it like that. And then the x and y's get a little confusing. Or we can do it like this. And the x and y's get a little confusing. But if I have it in my head about opposites and adjacents, I'm a lot better off. Okay? Because we can rearrange and reorient things quite a bit. But if I can do that, I can represent that off. So, if I do this, sine of the angle is going to be y over r, or opposite over my hypotenuse. Cosine of the angle is my x over r, or my adjacent over the hypotenuse. Tangent of the angle is y over x, or my opposite over my adjacent. And we can use this information to find out all kinds of stuff. So, let's take a jumbotron. And I've got my little person here, and you guys are all going to find out that I am not the best artiste. But let's say we know this distance. We're going to be 100 yards away from the bottom of our jumbotron. We can use our handy dandy cell phone, because our handy dandy cell phone is a good tool. And I can measure this angle. And we say that this angle is going to be 10 degrees. And I can measure this angle. And that angle, we're going to say, is 13 degrees. We want to know how big the jumbotron is. We want to know how big the jumbotron is. Well, this is a 2-equation, 2 unknown problem. Okay, 2-equation, 2 unknown problem. because this distance here, we can call it h. We know what the height is. We can call it h. So if I did this, I have the opposite is what I want to solve. I have the adjacent. So if I go back and I look at what I want, I have the opposite and I have the adjacent. So tangent is going to be my good thing. So I can say the tangent of the angle is equal to h divided by our d. But our h is the x that we want, and we'll have to give this another name. We'll give it a. It's x plus a over d. So that's my h. Now this one, tangent of my other angle, so this is angle 1, this is angle 2, is a over d. I have angle 1's known, I have angle 2 is known. My distance is known, x is what I want to solve, but now I can solve for a. I have 2 equations, 2 unknowns. You guys are going to be using 2 equations, 2 unknowns a lot. So that's one of those things you may want to go brush up on. So I'm going to solve for a. So a is going to equal my distance times the tangent of the second angle. I'm going to take that, I'm going to plug it into there. So tangent 1 of angle 1 is equal to x over d plus d tangent over d. Everybody see what I did? I just kind of broke it up. I'm going to solve for x, so I can do it a couple of ways. So I'm going to do d tangent angle 1 is equal to x plus d tangent angle 2. X is equal to d tangent angle 1 minus d tangent angle 2. Angle 1 was this whole h, so that's my 13 degrees. Angle 2 is my 10 degrees. So this is going to be my 100 yards minus the tangent of 13 degrees minus the tangent of 10 degrees. Got that, times 100. It's going to be 5.45 yards. So kind of looking at what we did is you draw a picture. I will tell you, in physics, drawing your picture helps tremendously. Okay? Because if you draw your picture, you can get things oriented the way you want them. You can see where all the variables are. You can see how those variables are taken into place. We used 2 equations, two unknowns. And this is a technique we're going to use multiple times. So if you want to brush up, if you think about, well, what math skills do I need to brush up on? That one right there. Two equations, two unknowns. We've already started building our reference sheet. And I would tell you, as you start working your homework problems, that's something that you may want to do. You may want to go ahead and say, okay, here I'm building myself a cheat sheet that I can use to have available to me when I'm working with all my problems. And one of the things that you would want to do is you can write up here, we'll start with our triangle. Get our triangle up here, this is R. And we have our Y and our X, and I know that's my angle. And so now I know the cosine of my angle is going to be my X over R, or my adjacent over my hypotenuse. My sine of my angle is my Y over R, my opposite over the hypotenuse. Tangent is Y over X, and that's my opposite over my adjacent. We can write down that R squared is equal to X squared plus Y squared, our good old Pythagorean theorem. We can do that. And then my normal vector notation is going to equal, there's my vector, is going to equal xi plus yj. And now I've started to build my equation sheet for physics. I've started to build my equation sheet for physics. So we can come back to this. And let's say we want to know the magnitude of this new a plus b vector. Well, look at my vector notation here. And we usually represent, if I want to say magnitude, I represent it like this. But that is just going to be the square root of this, my x plus c squared, plus my y plus d squared. If I wanted to look at the magnitude of A, just the magnitude of A, that's this, x squared plus y squared. All I'm doing is taking this notation, putting it back here, and using my right triangle. That's all I've done. The other fun thing is I can solve for this angle too now, right? If I have my x and my y, guess what? The angle is going to be the arc tangent of y over x. So I can go back and forth between this notation, and everything just by looking at it. I can go back and forth just by looking at it. So we'll utilize that function really, really well. I mean, that's just going to be something that you can play with. And again, you're already starting to build, your cheat sheet. Okay, let's talk about units a little bit more, and then we'll call it a day, because brains are full. I'm starting to see glazing. Starting to see glazing. Okay, so our fundamental units. Fundamental units are going to be distance, mass, and mass is different than weight. Weight is a force, mass is stuff. Distance, mass, time. These are typically in SI units are going to be meters, kilograms, seconds. Another fundamental unit we'll use, but we won't use it until physics 2, and that's charge. Derived units. Those are going to be things like force, which will be a Newton, which is going to be a kilogram meter per second squared. Velocity will be in meters per second. Newton is a weight. In the English system, that's a pound. English system, mass is a slug. Distance is a foot. Time is still seconds. That makes life really good. Another thing you'll want to put on your handy dandy cheat sheet is the acceleration due to gravity. It's going to be a constant. Gravity is a vector. And gravity is going to be, we're going to use 9.81 meters per second squared, or it'll be 32.2 feet per second squared. So that we'll be able to utilize that. All righty, questions? I don't see any questions in the chat.